All right, I'm going to give you guys a screencast here to talk about a specific topic in rotational motion, and that is a situation where you have rolling without slipping, like a wheel that rolls but it doesn't slip when it rolls, which is the normal, like your car tires, normally they roll without slipping. The only time they would slip is if you lock the brakes up, your anti-lock brakes don't work, and the wheels are literally locked in motion, you're sliding on ice. So most of the time you're rolling without slipping, but you'll see this phrase a lot in rotational AP problems, and so I want you to understand what they're saying when you read that. Let's say there's a point. Let's say a wheel is rolling like this. So I've got some, it's rolling in the forward direction. So the wheel is translationally moving to the right, but it's rotating clockwise to do that. So it's got an axle right there. It's in contact with the ground. Remember that when a wheel rolls, a new point on the wheel touches a new point on the ground. So these points are going to touch later on. And while it's in contact with the ground, that point in contact with the ground, the velocity is 0 for those points at that instant, just for that instant. So it's static friction that is at work when a wheel rolls without slipping. I just want to remind you of that from back in previous chapters, because this will make more sense to you if you think about, if you remember that as we go through the description. Okay, so let's look at another picture here, another slide, and this one shows that a round object, a wheel again, is rolling without slipping. There's a fixed relationship between the translational and rotational speeds. We've already seen this before. The tangential velocity is equal to r times omega. Here's what I want you to understand about that. There's a little more to this than meets the eye of what we've seen before. For instance, let's say this is rolling without slipping. You've got a contact point right here. As the wheel is rolling in one period, that's one period, so that's one full revolution, the distance it travels is one circumference. So this point is going to go all the way around here, and it's going to be back down at the bottom when the wheel is at this point over here. Let's call this point A, let's call this point B. When it gets to point B, it's made one full revolution. The distance it's covered on the ground, if it hasn't slipped, that's why it's such an important situation when it rolls without slipping. It's a special case where you know the exact distance it's gone when it rotates. It's gone one circumference. So you can calculate the linear velocity that way. Well, the whole wheel as an object has moved at that speed, but there's different points on the wheel moving at different speeds, believe it or not. The center of mass is the only point on the wheel, this axle right here, which is the center of rotation, I should say the axis of rotation, is the only point that's moving translationally at speed v at any given point in time. So let's go to the next slide and try and understand that a little bit better. So when we go to this slide, it kind of explains a little bit more about the situation. You've got pure rotation. So we can consider rolling motion a combination of pure rotation and translational motion. Pure rotation would just be a rotating wheel that's rotating in place with a radius r. We know that a point on the edge here, on any point on the rim here, has a relationship of the tangential velocity is equal to r omega. If it was moving in pure, so this is pure rotation, this is pure translation here. So if it was skidding across the ground, in other words, I'm just dragging it across the floor without any rotation at all, every point is moving with speed v. So you could say, well, if it was rotating, that velocity would be equal to the radius times the rotational velocity, omega. But literally every point, you see these green vectors all have the same length. They're all moving. Every point on that wheel is moving at the same speed. In the rotational motion up here, in the rotational motion, as this thing rotates, if it's rotating clockwise, a point at the top is moving to the right, a point at the bottom is moving to the left at that instant in time. The only point that's not rotating is a point that's perfectly on the axis right there. It's not rotating at all because the radius would be 0. So it doesn't have any rotation. It doesn't have any translational motion at that instant. So let's look over here. In this view, you've got something that's rotating clockwise. It's the wheel. It's a combination of these two motions. So if something's rolling without slipping, here's that point on the ground that's not moving at all. For that instant, the velocity is 0. The center of mass of the axis of rotation is translating exactly at r omega. So you can almost picture this as an addition of this green vector plus this green vector gives me that result right there. I add the two green vectors in opposite directions of equal magnitude. I get 0 velocity. I can add 0 here to that green vector right there, and I get that green vector right there. And on the top, I get two vectors pointed in the same direction. It's actually moving at a speed twice that of the center of mass of the axis of rotation. So a point on the wheel right here is actually moving faster than a point that's down here at the center, and much faster than a point down here on the ground at any given instant. That's because of the rotational motion combined with the translational motion. And you can almost think of this, there's another way to think of this, and that is, I'm going to erase some of the stuff right here so it's not so busy. Another way to think of this is this point being your axis of rotation. Since its velocity is 0, you can think of the point of contact on the ground. You know, you've got a torque being applied there. You know, you've got a friction force that's acting this way, causing this wheel to spin. And here's the distance r. It's spinning about that axis right here. So you've got a velocity r omega. So whatever the rotational velocity is, r omega is the velocity of that linear velocity of that point right there. And if I come all the way up here, this is 2r. So I've got 2r omega is the linear velocity of that point right there, caused by the friction force down here on the ground. Okay, that's a lot to think about, a lot of concepts there, but I'm going to apply it in an AP style problem on the next slide. Okay, this is one of the kinetic energy AP style problems that I have on Schoology for you to do, and it makes use of the rolling without slipping idea right here. So that's why I wanted to cover that before I had you do this problem. But you got a solid cylinder with mass m, radius r, and rotational inertia. See, they're nice. They give you the rotational inertia. You don't have to look it up on the table. It's 1/2 mr squared, which is what you would expect for a solid cylinder if you went to that table and had to find it yourself. And it's rolling down the inclined plane above. The cylinder starts from rest at a height h above the ground. The inclined plane makes an angle of theta with the horizontal. And of course, they want to express all solutions in terms of all that given information and the constant g. So they want you to determine the translational speed of the cylinder when it reaches the bottom of the inclined plane. So the translational speed would be v t. It's the same as the tangential speed. So the translational speed is just how fast is really the center of mass going. So they want to know when the wheel gets down here to the bottom, how fast is this point that's in pure translation going. You've got this point here that is at rest. You got this point here that's moving faster. The point right in the middle is the point that we're interested in. That's going to be the translational velocity. We'll do that in a second. Let's first do part B, because we can do that and then we can come back to part A. On the figure below, draw and label forces acting on the cylinder as it rolls down the plane. Your arrow should begin at the point of application of each force. So this is a little different because usually we're in previous chapters we just used a dot and drew arrows pointing away from a dot. Now we've got extended objects that have moments of inertia. We have to consider where the force is applied. I'm going to start with my gravitational vector, and I'm going to draw it down here. I'm just going to call it mg because the Earth acts as if all the mass is concentrated at the center of mass. This is a uniform cylinder, I assume, so it's uniform density, and the center of mass is right in the middle. Then you've got a normal force, okay? So the normal force actually acts right here on the bottom. Okay, so the normal force is going to act down here. Let me get my pen going, sorry. And it's going to act that way because this is on a plane, you know, so the normal force is acting right through that axis of rotation here. And then it turns out friction is the other force. It's static friction, and that's acting at that same point of contact, and it's at a 90-degree angle to the normal force. So that's what those forces look like when you draw them at the point of application. So that's not something we've seen before, but I wanted to draw that for you so you had some basis for this. All right, and then we'll come back and we'll also get the acceleration of the center mass while it's rolling down the inclined plane. Let's go back up and find the translational speed of the cylinder when it reaches the bottom of the inclined plane. The translational speed of the cylinder is something that we can do using a problem we can solve using conservation of energy. So I'm going to take this over onto the next slide. All right, so here we are. I got the picture here, and really all the given information is on the figure. I've added the only two things that I think I needed to add, which is they gave us that moment of inertia 1/2 mr squared, and they asked us to solve for the translational speed at the bottom. Okay, so we want to figure out how fast is this thing going when it gets down to the bottom here. So that's where we want to know the VT. This is a great application for conservation of energy. So whenever you have a rolling without slipping problem and they're asking about speeds at the bottom of a ramp, you want to think conservation of energy, and you've got two different kinds of kinetic energy. You've got rotational energy because this thing is rotating when it gets to the bottom, and you've got translational because it's also moving physically from right to left, you know, down the ramp. So think about the initial situation up here, the final situation down here at the bottom. So I'll put my initial energy on this side, I'll put my final on this side. I'm going to make an equation. Initial, the only kind of energy I have is, since I'm above a 0 point here, this is going to be my UG0 is going to be down here at the bottom. I'm H above that, so I for sure have some gravitational potential energy. So I have UG initial on the initial side, and on the final side I've got K rotational and K translational. I should put an S. Okay, so I got rotational and translational kinetic. What's this? This is MGHI. This is 1/2. Rotational is I omega final squared. This is 1/2 m v final. Actually, let me just say vt final squared, right? So that's the equation I'm going to start with. Now I'm going to start substituting in the variables that they've given me and simplifying some things here. So let's go, the mass of the object, little g times h, equals 1/2, and they told me this was 1/2 capital M, the radius squared. That's my I. All I did was substitute in this for I, and then omega F. So the final omega is equal to the translational speed of a point on the rim of the wheel divided by r. So we know that r omega equals vt. I just solved that for omega. Okay, and then we're going to substitute that in. So this is now going to be down here. VTF squared over r squared. Okay. Okay, here's why this works. Here's why the relationship over here works, Because remember in the previous slide about rolling without slipping, if I consider this my velocity 0 point, this is the point that's in pure translation, is this center of mass. I've got this omega right here. I've got a radius r of the wheel, and this point in pure translation is one radius away from the point that's not moving at all. So you can see that that equation is valid for this center of mass point right there, or axis of rotation. So that's why I can do the substitution step right there. All right, and then I'm going to finish this off. Capital M for the mass, and then VT final squared. So this is that last term is the translational kinetic energy. So I've got a whole bunch of terms right here that I can actually do some simplification. Surprisingly, mass shows up in every term, so I can cancel the mass out. I've got radius squared here. I've got radius squared in the denominator here. Those two are going to cancel out. So what I'm left with is GH equals 1/2 times another 1/2. That's still left right there. VTF squared plus 1/2 another VTF squared. That's from over here. So I'm going to have to find more space here. I'm going to shrink this down a little bit if I can. No, I can't. It's going to be a mess if I try and do that. Okay, so I'll just squeeze it in down there at the bottom. So moving over here, I'm going to combine these terms. I get GH equals 1/4 VTF. Well, actually, let's just add that up. This is 1/4. This is 1/2. You add a half to a quarter, you get 3/4. So this is 3/4 VTF squared. So solve that for VTF squared coming up here. VTF is the square root of 4/3 GH. Now, before we go any further, let's talk about the significance of that, because that's a pretty interesting result. Because we know if we dropped an object from this height, I'm up here at the top again, from a height h, if you use kinematics and you drop something from that height, or if we just assumed it slid down there and didn't have any rotational action at all, just sliding, velocity final is root 2 GH. Well, this is root 4/3 VH. 4/3 is less than 2, right? Because 2 would be 6/3. So I've lost, 0.67 out of 2 in square root of that for my tangential velocity, which makes sense because some of this initial gravitational potential energy goes to getting the wheel to rotate. The rest of it goes into the translational kinetic energy. So that makes sense that the 4/3 under the radical is less than 2. Okay, let's try the next part of this problem, and then I'm going to call it quits on this screencast. So we're going to go back to finding the acceleration of the wheel. Okay, in part C, they ask us to find, the acceleration of the center mass of the wheel. So what they're asking for is the translational acceleration. When they say the center of mass, that's the only point on the wheel that's moving in pure translation. So they want to know what's the translational acceleration in terms of all these variables that we just determined. So to do that, there's two ways to approach it. You can use kinematics, because you now know that VT final is square root of 4/3 GH, and you've got initial velocity of 0, and you know that the distance that this is going to travel is, opposite over d. So d is equal to h over sine theta. So you've got an expression for the distance it's going to travel, you've got initial velocity, you've got final velocity. That's enough information for you to use a kinematic equation, Mr. Fantastic, to solve for AT. Instead of doing that, and this is actually capital H here. I'm not very good at following my own advice of using the variables that they give you. The other way that I'd like to show you is using our free body, our force diagram, and Newton's second law. And I'm going to draw that force diagram again here for you. I got the normal force, we've got the friction force, and we've got mg. So if we wanted to use Newton's second law for rotational motion, okay, torque equals I alpha, and the only force that's producing a torque about this center of rotation is Fs. It's the only one that's actually producing a torque. It's one radius away. That's the lever arm. There's your 90 degrees right there. So it's producing a torque of the friction force itself times the distance away from the axis of rotation is r equals the 1/2 mr squared times alpha. Has that relationship with tangential acceleration, the same as omega has that relationship with velocity from the previous slide. So I just did a substitution in for alpha. I just did a substitution here in for I. And on the next slide, I'm going to do a substitution in for Fs, and then I'm going to come back to this one. I don't know if I can do that with this software. Okay, if I want to finish this problem, I've got to solve for, I'm trying to show that AT is equal to 2/3 of G, oops, sorry. Sine theta. So I got to get rid of this Fs. As you can see, the R's are going to cancel out because there's an R here. When I divide it over to this side, I'll get an R squared. There's an R squared there. So these guys are going to cancel out. So I've got the 1/2 and the m, and I've got to figure out how to get rid of those. But I'm going to go back to my original force diagram, and in the x direction, so I still have my skills from back in chapter unit 5 or 6, where I know when something's on a ramp, I can sum the forces down the ramp in the x direction, and I've got a net force in the x direction, even though I've drawn my force diagram like I did with the forces at the point of application. I still know that in the x direction I've got a net force of mg times sine of theta going down the ramp. That's the vector in the x direction down the ramp right here, minus the friction force the other way is going to be equal to my net force. So I guess I should write it this way: mg sine theta minus Fs equals mass times the tangential acceleration of the object. Solving for Fs, it's equal to mat minus, oh, other way around, sorry about that, mg sine theta minus m at. So I'm going to substitute this in up here for Fs, and now I can solve that. mg, let me use the variables that were given to us in the problem. M, capital M, G, sine of the angle, minus M at equals 1/2 M at. M's in each term, those cancel out. Get my A terms on the same side, so G sine theta equals 1/2 AT, because my M is gone, plus AT. Factor out the AT, G sine theta equals 3/2 AT. So AT is equal to 2/3 G sine theta. So I wanted to show you that problem because I wanted to use the force diagram to do it. If you remember, we could have used kinematics. It was probably a little bit easier using kinematics. It was probably a lot easier to do kinematics, but I wanted you to see this worked out using Newton's second law in linear fashion to actually go back and create this equation here, which we haven't done in a long time. Hopefully this helps you finish the problem. Now you're going to be asked to find the coefficient of static friction in the next part, but I wanted to give you a little hand on this and have you see how it's worked out with a problem where an object is rolling without slipping. Questions, please, from 9 to 10 o'clock on Tuesdays and Thursdays. There's a Google Hangout. You can connect with me and ask questions. Okay, guys, good luck. Stay home and stay safe.